Uh, Today, Yannick Hold is going to be talking about parallel programming, and his topic today is once you scoop, no need to fork. Okay.
Thanks. Thanks, Simon. First of all, I want to thank every one of us for being here today. I'm really proud to be being in front of you today to present you my presentation, Once You Scoop, No Need to Fork. So I'm Yannick, as Simon said, and I'm currently doing a master's degree in electrical engineering at Laval University back in Quebec City. I think I'm the only representative of Quebec City back here in PyCon, Canada. And I hope we do pride. You're from Quebec City also? Oh, good. We're too. Nice one. So, we'll dive in the subject. Today I'm going to talk to you about what is the future. I'm going to talk to you about a project that assesses that future and then a roadmap for the future. So a big question everyone can ask himself is, what is the future? So we're going to take the glasses of the past to better see the future, to realize that in 2000, we've hit a wall considering the microprocessor frequencies. The speed of computers are not the same as today. What I mean by this is that before the year 2000, if you wanted the software to be twice as fast, you just waited, because there would be a new chip going on, and you don't have to write software. It's going to be twice as fast in like 6 months. But since the 2000 era, you gotta have to take into consideration new aspects of how we're developing, such as parallelism. Parallelism is something that is real in every scale of computing. Let it be inside computers, inside the processors, the new ARM have multiple launching sequences, to global systems such as supercomputers, and now we're talking about cloud computers. So all these things are kinds of parallel programming. So if you want to make a good use of this future, of this kind of characteristic of new hardware, you want to have a framework that works in this philosophy. So you want something that is simple, robust, and that scales well, and that is versatile, that can accept anything of any type of data, or any type of conjunction of mixing toward one another. That's why we've developed School at our laboratory. So Scoop, I'm a main developer of this package. It's available on PyPI. And actually, it's open source. You can get it from pyscoop.org. It's actually a redirection to Google code. So what is Scoop? We're making this package upon 3 tenets. These 3 tenets are: the future is parallel, simple is beautiful, and parallelism should be simple. And I've just read out loud a slide to you. Sorry for insulting your reading capabilities. So these are the main tenets that when we write the code or when we design API, we want these 3 tenets to be true. So our main target audience is mainly researchers or people that are in the scientific era, or students and academics. From what I understand, you may not be quite the target audience of my kind of project, but who knows? Maybe you'll be interested by it. So everything is open source. You can download it freely, and you can hack inside to see how we do things. So it's not only about science, it's also about how we realize that kind of stuff. So the building blocks we use to make Scoop is 0MQ. I've seen that you've already had a talk about 0MQ just about earlier. That's an amazing package. We use it to handle every communication in our program. So it's amazing. It works. It's really simple to use for us. So it creates code that is easily maintainable. And the second building block we're using is greenlets. Greenlets are actually a spin-off of the PyPy's stackless, not stackless, but micro-thread systems. So we're using, basically what we're doing is taking your programs, your functions, your sections of program, we're encapsulating them in Greenlet and pass them around using 0MQ. So you're going to say to me, it's really easy. Why are you saying a talk about this? Well, it's not that easy. So one of the main tenets of Scoop is simplicity. So to be simple, we want it to be based on something that is standard. Nothing is more simple than being based on a standard. So we use the PEP 3148, which specifies the futures. It's coherent with Python 3, and actually it was implemented in Python 3.2. So it's really some base upon which we base our whole thinking about how we implement our APIs and how we exchange stuff with your programming, with your programs. So the supported environments of Scoop is pretty much everything. Actually, if 0MQ runs on your system and Greenlets too, well, it works on your system. So we've got user stories that shows that macOS, Windows, and Linux are working pretty well, as well as environments larger than only an OS, such as supercomputers, laboratory of computers, and even a cloud-based system. So one cool thing about Scoop is that it has great versatility. So once you're at the top of the hierarchical task, you're the root. Actually, you're your own program. So when you launch task around, if you're using, for instance, multiprocessing, you're stuck with one level of parallelism. You cannot launch multiprocessors inside multiprocessors. Actually, with Scoop, you can do that, and you can do more. You can launch functions that are different in size, in time, in data sets, and even by nature. You can pass around multiple functions and spawn different functions inside a function, and it's going to work, no problem with that. So it has a great versatility compared to like multiprocessing. And the cool stuff is that it even works with computers linked together with the internet, which multiprocessing is really hard to get on with. So we are using a broker architecture, which is basically everybody is connected to a single broker. Nobody is connected together. So you're going to say to me, that's a standard master-slave configuration. Well, actually, we've changed a bit of this philosophy. We've made that the real master is actually a worker. We wanted the broker not to be like where the data gets strangled because there's too many connections. So actually, the broker in the middle of every communication is blind. It's dumb. It's really dumb. Actually, it only receives things and passes it around. So the intelligence is in the worker, is in every worker. So when you spawn tasks and you map things around, you're actually on a worker, and the worker says, oh, I want to spawn things, and can you pass it around, please? And if you want to spawn something inside one of your already spawned tasks, another worker will become the father of a new tree, and you can go on like this. So that's really cool because the broker isn't like a problem by I/O communication, because it's really dumb, so it doesn't do anything aside from passing things around. It doesn't do computations nor serialization, so it's really fast. So one thing one technique that we are using to speed up our parallel distribution system is that we use queues or buffers inside every worker. So each worker have a high watermark and a low watermark. These are simply two marks that says, hey, the high watermark says, hey, I've got too many data. I don't need these extra data. And the low watermark says, well, maybe it's time for me to get another set of data. So once you begin a worker that isn't the master worker, the root worker on the previous slide, initialize by talking to its broker saying, hey, have you got stuff for me? And then it goes up to the high watermark, and then you realize that I forgot to bring my laser pointer. And So you get to the high water mark, and then you simply start to compute things. Once you go to the low water mark, you realize that you're going to run out of stuff, and you don't want to end up waiting about communication, so you start computing something while already sending data request for more information to crunch. A cool thing is that in the stable version of Scoop, as it is already done, these are just plain numbers, but in the newest version, the version that is 0.6, that will come out soon, it's in release candidate state, it's in seconds. So it's really cool because it makes packages of like 1 second of data, of computation, of 2 seconds of computation, and you don't have to specify anything yourself. So one cool thing about the future API that we implement is that it's simple. So all you have to do is use our API, and then you have a free parallelism happening to you. So you can simply have a map function, you pass your function around in your data set, and if you want to have finer granularity over your project, over your hierarchical tasks, you can submit one after another. And we are currently working on a MapReduce to beat the famous Hadoop soon enough, I'm sure. So here come the examples. So here's an example if I want, for instance, to load multiple websites. So people were accustomed with HTTP processes know that I use this example because it's an IO-bound problem. You can send multiple requests together, and it's going to be faster because of the way of the TCP/IP sockets works. So here's how you're going to do it if you're going to do it in simple Python. So you simply map a list of URLs to your function that simply gets stuff. And if you want to do it with Scoop, the only thing you have to do is to import Scoop and then use our map function, and there you go. If you're on a single computer, it's going to use all your cores to make things at the same time. And if you launch Scoop using multiple computers, it's going to fetch with every resources available. Another example is if you want, for instance, to take the example of multiprocessing that is on the Python documentation. You know that it's 2 lines, one to create a pool of workers, the other one to simply map around your data upon this pool of workers. So if we scoop it up, it's going to end up in simply one line that says future.map. The list around is a little rant by me. It's because in Python 3, the futures.map, actually futures.map is from Scoop, but in Python 3, the philosophy is about returning generators. So you must wrap it around a list to get the actual data, otherwise it's going to be a generator. So if you want to hear a random rant, please make your software Python 3. So aside from that, if you want to have like finer granularity over your systems, you can, for instance, if you have a function that may take from 1 second to 1 hour to complete, but you want to get the information as soon as they arrive, you can simply, that code seems complicated, but all it does is on the center loop, submitting functions, parallel functions one after the other, and then at the end line, it simply says, return them to me as completed. So as soon as one gets completed, even if it's the last one in the data set, you're going to have it back in first. So Scoop is actually a work in progress, so you should expect these kind of things to be like really simpler in the future. So how do you start Scoop? Well, actually, it's pretty simple. It's exactly like C profile. You do Python -m Scoop, your program. That's it. If you simply does that, it's going to take every core on your computer. If you're on an 8-core computer, it's going to take 8 workers. spawn a broker and simply pass things around 8 times as fast. If you're on a supercomputer using, for instance, SunGrid Engine and Moab and things like that, you simply have to use Python minus mscoop. As you see, it's exactly the same thing. Scoop is going to realize that you're on a supercomputer. It's gonna recognize the environment, take everything you've scheduled, and then use every resources available to make your program run fast. And if you're on a LAN system and you want to use multiple computers, you simply pass around the variable minus host, and then IP's address or DNS addresses. We also have forecasted like network configuration file to pass around to be simpler than using command line startups. So the question I get often is Scoop working? The answer is, I think so. Well, actually, I've made an example on a supercomputer in Quebec City, the supercomputer of Université Laval. And then on the black line, you've got the optimal speed up. If everything was like really optimal, twice the computers does twice the job. And in blue, you see the speed up that we achieved using an evolutionary algorithm program. So with 256 cores, we achieved like 230 something times the speed. So that's pretty much efficient. We want to be as efficient as possible and keep it as it for the future of Scoop. One cool thing about Scoop is that it's inherently load balancing its system. Now is a really complicated graph that I wanted to show you, simply to show you that most of the time everything is green. Green means 1, and 1 means there's something that's running on it. So all this graph represents is that on every workers, every line you see on the left is a single computer. So there was, I think, 64 computers on this run. So every 64 computers was working to get the job done. The red line is only the root worker, which has 2 program running at the same time, because you have the root program, which is waiting for all the subsequent program, and is also working something. The blue lines are simply because it was an evolutionary algorithm that was running, and the blue lines are only the mutations that are serial. This is inherent to the problem and not to the system, the Scoop system. So our roadmap for the next couple of months are to add collective operations such as MapReduce or MPI-like functionalities, such as scatter, gather, and this kind of stuff. Also, we want to get global variables handling, like we want to be able to share states between each workers. We want to be able to control resources, make groups, or split our pool of workers between some works we want to do. And one really important but really hard thing we want to do is add fault tolerance, robustness, and also support to online cloud services. So thanks everyone for listening to me today. I want to thank the YLVSN team, which helped me throughout the summer for this project. Don't forget that the future is parallel. It ought to be simple. And don't be shy. Drop by our mailing list if you want more information. If you found a bug, we're also open for any kind of review or feedback. Scoop is a work in progress, so we're open for every kind of feedback. So thanks for being here, and well, have a nice PyCon Canada. Is there any questions? Yes?
Do I understand it correctly that it's conceptually similar to what is PyCloud trying to do commercially?
You're absolutely right. It's similar, but the thing is PyCloud is a service-bound. It's like a closed thing. I know it's open source, and I've only learned about it like a few weeks ago, which is really sad. But I'm actually wanting to like stole some of these ideas into my project. But the thing is, I think the goal is inherently different from PyCloud to my project, because my project is aimed about having something at your level, like your supercomputer, or if you don't have access to the internet, while PyCloud is something open. So my subject is also for like closed data subset or things that are could be not open to public, things that cannot run onto the cloud.
Thank you.
No problem.
Okay, thank you everybody, and that concludes this presentation. And if you have any more questions, Yannick will be hanging around.